In this installment, we're going to look at the last of the one-dimensional vertical projectiles, which is when we've thrown the ball upward. So again, we have our 24 kilogram rock, which is irrelevant. It's thrown upward, same 100-meter cliff with initial speed of 7.0. So that means a V0 of positive 7.0 meters per second. We have our same questions. When will it hit the ground? What will its impact velocity be? Now this one is a little bit different than the others because this one, we throw it, is going to go upward. And then it's going to come back down and hit the ground. Now, what is customary when we're doing these one-dimensional things, it will actually travel upward and downward on the same path. But to see the dots, we will draw them just slightly next to each other. So it'll look like this so that we can see the up and down part as opposed to this. So this really means this. All right, so if we think about this thing has to go up, then come down. So we might expect this to take longer than if we just dropped it. So whereas we had times 0, 1, 2, 3, 4, 5, it took nearly 5 seconds on the way when we dropped it. We know it's going to take probably at least 6. Let's see how that does for us. So our acceleration, again, is a constant minus 10. And the instantaneous velocity, well, is plus 7. It's 7 when we start. And so if it changes by minus 10 after 1 second, it will be minus 3. And then minus 13 and minus 23 and minus 33 and minus 43 and minus 53. This first step is the one that throws people for a loop. 7 minus 10 is minus 3. Minus 3 minus 10 is minus 13. It's all the same when it's the same size, same side of 0. But when we're crossing positive to negative, it can throw people. But the process is just the same. We're just subtracting 10 every time. Now, the mean velocity up to this point, well, has no meaning for the first times 0 because no time has passed. So plus 7 minus 3 is 4 divided by 2 is 2. 7 minus 13 is minus 6 divided by 2 is minus 3. 7 and minus 23 is minus 16 divided by 2 is minus 8. So you'll notice this is changing by minus 5. And if we were to test that, V bar equals V plus V0 over 2, and we're to use our minus 53 plus 7 over 2 is going to give us minus 46 over 2, which is minus 23. And indeed, that is what we get. Our displacement, again, is average velocity multiplied by the time. So our displacement is 0, 2, minus 6, minus 24, minus 52, minus 90, minus 138. V bar delta x delta z is v bar delta t. Our average velocity of minus 23 times 6 is minus 138. So those are our displacements. And now we can tell minus 100 is going to be pretty close to 5. So we were correct, it's going to take longer, but closer to 5 than to 6. So we might say, it's a little bit hard to estimate here, but we might say maybe it's 5.2 seconds, maybe 5.2 seconds. And the impact velocity will be close to minus 43. Oh my gosh, maybe the impact velocity will be minus 45 meters per second again. Maybe. So these are the approximate estimates we can get from the table. About a little over 5 seconds, about 45 meters per second again. So for our analytic solutions, velocity is minus 10t and our initial velocity is 7. So there's our equation that will give us the instantaneous velocity at any time. Our vertical position, z is 1/2 the acceleration minus 10. Our initial velocity is 7. And again, our coordinate system we set up will make this 0 and that minus 100. Positive direction, negative direction. So our z0 is 0, giving us an equation of z equals minus 5t squared plus 7t. That's the z of the rock. The equation for the ground is again a minus 100. So we're looking for when these two intersect. Now we can go to our graphing calculator. Lo and behold, instead of it being minus 7x, it's plus 7x. Oops. And we zoom out, and let's look here. Oh, so let's see. Notice there's this portion of time where it goes above the ground. But again, we have a downward cut parabola, and we look at the time. We zoom in for that intersection, and we can see. So that is between 5.2 and 5.3, a little more than 5.2, a little less than 5.25, maybe 5.22 seconds. 5.22 seconds. So we'll have, when does minus 100 equal minus 5t squared plus 7t? Well, we'll say t is 5.22 seconds. And if we have two significant digits here, then we'll report a 5.2 seconds like so, and not box our 5.22. Our 5.22 is our unrounded answer, and then our boxed answer is 5.2 seconds. But we record our unrounded answer so that we can use the unrounded answer in our calculation of the velocity. So minus 52.2 plus 7 is going to be minus 45.2 meters per second. Minus 45.2 meters per second. So it's interesting in making comparisons that when we had our rock and we dropped it versus throwing it downward versus throwing it upward, the time we had of throwing it upward was 5.2, throwing it downward was 3.8, and dropping it was 4.47. The impact velocity, 45.2, and I believe our impact velocity was 45.3 when we threw it downward, and it was 44.7 when we dropped it. Not a lot of difference in the impact velocity for these three scenarios, but a much more noticeable difference in the time. Now, again, we could graph these. Our graphs, velocity time. The one we just did, we have a y-intercept of 7. And again, the things we can read are velocity time, the slope, delta v over delta t is the acceleration in the area, is v bar delta t, which is the displacement delta z. So this is for our v0 equals 7. We had said that our v0 minus 7 looks like this. And our v0 of 0 when it's dropped looks like this. The three lines are parallel. This one shows a negative velocity being thrown downward. This shows a 0 velocity being dropped. This one shows a positive velocity. The velocity decreases from 7, 6, 5, 4, 3, 2, 1, 0, and then becomes negative. This is one of the most non-intuitive graphs that people have. You expect that when something is being thrown up and coming down, that there'll be an up-downness to it. Well, this graph shows clearly it just going down, because the slope is the acceleration, and the acceleration is minus 10. The velocity is actually it actually decreases to 0 at the top. That's what this illustrates at the top. When it's thrown downward, there's no time where the velocity is 0, or dropped, excuse me, except when it starts at 0, and there's no time at 0 when it's thrown downward. So these graphs here are a little bit difficult. This is a thrown upward and reaching the top and coming down. This is a thrown downward, or excuse me, this is a drop because V0 is 0, and this is a thrown downward. It has a starting velocity of -7. This is V0 equals 7. This is V0 equals 0, and V0 equals -7. Now let's go to our ZT graph, like so. Let me just redraw that. Don't like that. So we know it took 5.2 seconds for it to reach a position of -100. So this is our -100 getting to there. The other one we had took 3.8 seconds, and that was the fastest it took to get there, and that was the gray one. And then we had our intermediate one, which was dropped, and that took 4.47 seconds. So we have the longest time being the flattest parabola, our shortest time being the one thrown downward, looking like so. Now, just a rough sketch without numbers, these three functions look the same. If you were given this graph and said, which one is the case of it being... I actually have to correct that. I am sorry. I got ahead of myself. The blue one actually slightly goes up and then comes down. And it reaches this point where there's a velocity of 0, which is right here when it reaches its high point. Both the thrown and dropped start at a z of 0. It's the one thrown upward that develops positive z's and goes like this. Now, we could answer a question. And the additional question is, when does it reach its peak? Well, its peak will be when the velocity is 0. So v equals minus 10t plus 7. When does it equal 0? We have 10t equals 7. T equals 0.7 seconds. So we can actually put a number on this, 0.7 seconds. That's how long it takes to get to the top. And of course that makes sense because the velocity should change by 10 in 1 second, and this is less than 10, so it would take less than 1 second to reach the top. And that, my friends, is how we do a one-dimensional projectile thrown upward, both with a table and analytically. In our next installment, we are going to look at an overview of the two-dimensional projectiles and look at the first of the two types.